Hello my dears. So in the last class we discussed about the fabrication of IC, right? How these ICs are fabricated and the detailed explanation and everything, right? The fabrication process completely we explained. And to add on with that, we have to look for how can we implement each component like diode, resistors, transistor, capacitor, etc. on the symbol or the single small crystal, that is the IC chip. How can we implement each component there? How can we implement each component there? That's we are going to discuss now. Okay. So first of all, we have to discuss how we can implement a diode in the IC chip, right? Chip is the smallest unit in the IC where we can implement a component, right? A component in the sense what? A diode or a resistor or a capacitor. Not two capacitor, two resistors. A capacitor, a single element can be implemented in a chip. Number of chips are formulated or joined together, interconnected together to form an IC package. Okay. So first of all, we have to discuss how can we implement a diode in a chip. So a chip is nothing but, my dear, what? A P substrate will be there. So the last step now, epitaxial N layer formed. Over that SiO2 layer also formed. So I will mark that also. This is the substrate. This is the epitaxial N layer, and this is nothing but, my dear, SiO2 layer. So this we already discussed it. Up to this we already discussed it. How we arrived in this step. Okay, that we already discussed it. So from that we are going to discuss more. Okay. So what is the next step means? We have to etch the two portions, I mean the two corner. So the edge of the two corner means you have to etch here and you have to etch here. Okay, and add pentavalent impurity to the etched portion. That means if you etch the SiO2 layer, etch means nothing but simply remove. Just you wash out the SiO2 layer. That's all the meaning of etching. So if you wash out this corner SiO2 layer, then below portion will be again the N layer. Na? If you wash this region up to this region, if you wash out, I will tell you now. Okay, for your simplicity I will tell you. So this is the meaning of etching. So if you etch this portion and this portion, again the below portion is again N, this also N. So for that we have to add more pentavalent, here it is a pentavalent impurity, right? We have to add more trivalent impurity to this etched portion. Okay, we have to add. If I write the steps also, my dear, this will be very big. So you write in your own language the steps. So first of all, we have to etch or wash out the SiO2 layer, and after the washed portion, there you have to introduce trivalent impurity. So trivalent impurity, if you add here, my dear, if you add here a trivalent impurity, more trivalent impurity, the region just below this will be converted into P, because we added trivalent impurity. So the region just below this will be converted into again P type. That is why here also P. That is why here also P. So the complete thing will be P now. And we formed an island of N region below this SiO2 layer now. So we formed an island of N layer just below the SiO2 line. Is it clear? And next step, this portion is again exposed, right? After we injected some trivalent impurity and made the complete region P, the remaining this portion, it is still exposed to sunlight, still exposed to moisture, still there will be chance of contamination. Still there will be a chance of contamination. So what we have to do? We have to completely pack again this region with SiO2 layer. For that we have to simply forcefully add some oxygen on the surface of this, will simply form SiO2 layer, that's all. So again we packed the whole with SiO2 layer, so that we packed completely. And now the next step we are doing, we have to make a small hole on this SiO2 layer. It is called a window. We have to make a small hole or small region on this SiO2 layer by etching. Etching means simply removing. So the etched region now called as a window. The etched region now called as a window. So to this window, so this window is again what? Exposed. We can see the end here. We can feel the end here because it is exposed to the atmosphere. Is it clear? So what the next? See, through this window, we have to add a trivalent impurity now. So on the top of this end, we have to inject trivalent impurity. So what it makes? Already it's N. If you add trivalent means that N will become converted to P, a portion of N only, not the complete N, but where we are injecting, that region will be converted into P. So what happened? Not the whole N, but a small portion will be converted into P. Is it clear? Did you get what I am saying, my dear? Did you get what I am saying? So the whole, not the whole region, but a small region will be converted into P now. Converted into P now. See the miracle now. It will form, see, P now. Is it clear? So what happened finally? Again this region exposed now. Again we filled with SiO2 layer. So now this will be act like the substrate. Leave the substrate. Substrate we can't consider. Substrate is the basement, just basement. So now it will become NP, PN diode, PN diode. See now, it will form a PN diode. Is it clear? It is internally formed. But how can we make an external connection? How can we make an external connection? Again we have to etch. Again we have to etch where we have to take the external terminal. So again we have to inject or simply drill or simply etch a portion on P, another portion on N. The two portion on P and N. It will form a terminal 1 and 2. The terminal 1 is P, the terminal 2 is nothing but N. Thus formed a PN diode. See, thanks to the microelectronics, my dear. Thanks to the microelectronics and the micro construction. See how beautifully it created a PN junction diode now. How beautifully it created. And the cost, see, simply we need oxygen and a etching tool. That's all. Oxygen, etching tool and an impurity. This is a very but less cost, right? A very cheap construction, right? That's why the ICs are very famous nowadays. That's why. So this is how we created a PN junction diode. Is it clear? Is it clear, my dears? You have any doubt here? You have any doubt here? Okay. Now, how can we create a transistor? How can we create a transistor? So the region, that means up to this P substrate N and P now. P substrate N and P. Up to this, the same for transistor also. So I am starting my process from this figure. So this figure I draw once again here. Okay. So NP diode. So up to diode it is already. So from this I am starting. So this is the PN diode again. Okay, fine. Transistor means nothing but, my dear, NPN. So N is there, P is there. One more N is we should need, right? So what we have to do? Again we have to make a window on P layer. So a window on P layer. And we have to add some pentavalent impurity there, not the trivalent. We have to add some pentavalent impurity to this window, which makes a small region on this P layer to N layer. Not the whole P region, but a portion where we much more injective. It is very similar to that. You can take a natural example. In a market, suppose we are going to buy fruits, the injected portion sometimes in some fruits, it's evidently clear, it's very clear there. The injected portion, we can easily visible, we can easily see that, because that portion will be darkened, that short portion will be discolored, not the entire apple, not the entire orange discolored, but a portion where we injected discolored. In similar manner, a portion where we are etching completely, injecting the pentavalent impurity, that region only converted to N, not the entire P. So this will be the structure. NP, a small portion, N again. So now we have NP and N, again SiO2 sealing. After that, see, 3 terminal, one from N, other from this P, other from this N. So you have 1, 2, 3. You have 1, 3 and 2. So emitter, base and collector. Emitter, base and collector. Is it clear? Thus we formed a what? Transistor. Thus we formed as transistor. Now we are going to discuss how can we implement resistors and capacitor, right? So for the same procedure, my dear, resistor also, we formed a epitaxial N layer, we etched this portion, we added some trivalent impurity so that the complete P will be formed. Up to that there is no change. And after that we are making a window. A window is made there, and through this window a trivalent impurity is added, so a portion of this N will be converted to P. A portion of this will be converted to P. This P region on which we have to drill for connection, H for the connection. So this will be act as this one terminal, this is 1 and this is 2, my dears. So this one terminal through this P, again the other terminal. So this is 1, the P region will be act as a resistor of resistance R there. Why I have chosen this P instead of that N? Because N contain lot of free electrons, so the resistance will not be there at. Okay, the resistance will not be there because it contains enormous amount of free electrons. But P means are holes. They are holes. The holes less mobility. The holes have less mobility than the electron, so that the conduction due to holes will be very less that compared to the electron. So the conduction is less, mean resistance is very high. So a perfect area for making a resistor is nothing but on P, not on N. Okay, otherwise it here itself I can make a two terminal, drill two terminal, and here itself we can make drill two for two terminals, and we can take it outside as the resistor now. But we are doing for P now, not N. So that is how we formed a resistor. Now we are going to move, how can we form a capacitor? It's also very interesting. So this etched portion again clean out. It will form like the same figure, exactly same. Now we are immersing or drilling or etching a portion for the terminal. In one region we inserted one plate of capacitor or one conductor simply. The other plate now, it is larger than the first plate. It is larger in thickness as well as the larger in length also. Okay, that's meaning of larger. Area of cross section as well as the width also very high. Larger. So that's why it is more penetrated. Two is larger, one is smaller. And see my dear, again two conducting region, one conducting, two conducting. This is external supply now, this is external. So two conducting region are separated by an insulator. This is the insulator. Is it clear? So two conducting regions are separated by an insulator. Insulator, my dear, insulator. Okay, two conducting regions are separated by an insulator. Okay, there we form a capacitor. And the capacitance value is depend upon dielectric constant of SiO2, because in between these plates na SiO2 there, right? In between this place SiO2 there. So the dielectric constant of SiO2 and area and thickness of smaller plate, because smaller plate is common for the two plates now. The smaller area is common for this area. The smaller thickness is common for this thickness also. That's why it is the dielectric constant of SiO2. The capacitance will be depend upon again the area and thickness of the smaller plate. That's all. So that's how we can vary the capacitance. And you have to note one thing, that it's not beyond 30 picofarad. That also you should note. Not beyond 30 picofarad. So that's how we created resistors and we created capacitors, my dear. Okay. Is it clear? Is it clear, my dears? Is there any doubt? Okay. That's how we have implemented components on what? Our IC. Okay. So now we are going to discuss a very important table. This is very important. Maybe this figure may be asked for examination. Okay, or the full form may be also asked for examination. So the scale of integration, abbreviation and number of components. So scale of integration means how much we integrated the component, that's all. It is called a small. When it is small means SSI, small scale integration. SSI means small scale integration. Okay, and normally for that small scale integration of ICs, the component number will be 1 to 20 components only. They mean total resistor, capacitor and a transistor, diode, everything. The total component count will be simply 1 to 20, that's all. Next one is medium, means MSI, medium scale integration. The component number will be 20 to 100, 1 to 20, 20 to 100. And next is very easy to remember. Medium, large, very large, super large. So medium after large, so large scale integration. So it will be 100 to 1000. After large, it's very large. So VLSI, popular name. You have heard this name for years during BTech, right? VLSI, very large scale integration. So the component range is this method. So this is very, very important. 1000 to 10,000 number of components are there in the VLSI IC. Okay. Next one, super large, recent technology, SLSI, super large scale integration. 10,000 to 1 lakh. That much component will be there. 10, 1 lakh. So 10,000 to 1 lakh component will be there. So this is very, very important, very large. VLSI now, it is very popular and it's very important. And there are two types of IC packing. These are IC packing. There are two types of IC packing. One is, my dear, hermetic IC. Hermetic IC means the IC is made up of metal or ceramic with glass. Metal or ceramic with glass. IC packing. Packing means outer covering. That's all. Outer covering of IC. Inner of IC is simply silicon and oxygen. There is no change in that. Okay. And the outer packing means nothing but the outer covering of IC. And next one is non-hermetic. Just remember this name. Purely plastic. So this will be costlier ICs. Hermetic ICs are very costlier because it contains metal or ceramics with the glass. This is simply plastic. Cheap ICs are non-hermetic ICs. So non-hermetic means simply made up of plastic. It's a very cheap ICs. Okay, cheaper ICs are there. So that is the classification of ICs, right? Classification of ICs. Okay. So now we are going to look very important ICs, some important ICs. Later on, if you study during our study, some more ICs you will be familiarized. You can add to this table, this topic. Okay, again you can add this topic. So leave some space there. Okay, you can add later. LM309 is nothing but popularly 5 volt voltage regulator. LM317 is nothing but adjustable voltage regulator, same 5 volt. Okay, adjustable voltage regulator. 555 timer you already know, monostable or astable multivibrator. IC741 you know, it's an op-amp IC. So that's all about IC. So IC is a specific topic in the sub-engineer examination syllabus. That's why I took this. So next we will discuss with a new topic in the next class. Okay, thank you.